I'm recording.
Like that makes a difference.
I know, but okay. All right. So far we've been focusing on really general first order systems, whether linear or nonlinear, and there's a lot you can figure out about even nonlinear systems. But now we can just get more in depth by assuming everything is nice and linear. Things just work out better, or more conveniently anyway. So, for a system of linear first order differential equations has this form. So I'll start by writing out everything in longhand, which is kind of a pain, so we won't do it very much. Okay, so we have component functions, x1, x2, and so forth down to xn. So we'll have the derivatives on the left side. And on the right side, we have coefficient functions times each of these variables. And it's just a variable by itself, x1. You cannot have like x1 squared or e to the x1 or anything like that. These coefficients, the a's, can be any functions of only t. They can't depend on the x's. So that's what makes the difference between a linear equation and a nonlinear equation. And then after we have these linear terms, we might have an extra function of t, like a separate term on the end for a non-homogeneous case. So this continues with the second equation. Whoops. All functions depend on t. I forgot to write the t dependence in this last column here. Okay. Now, if you look at the coefficient functions, notice they all have two indices, I and j. So the first index, the I, always refers to the equation. So notice we have 1, 1, 1, 2, up to 1n for the first equation. We have 2, 1, 2, 2, up to 2n for the second equation, and so on. And I can keep going all the way down to the bottom. So a n1 x1 plus a n2 t x2 plus a nn n of t. All right, so the first index deals with the equation. The second index indicates which of the unknowns that coefficient is multiplying. So, like, notice here we have a1n xn, a22 x2, and so on. So that's the convention that's being used for numbering these all these coefficients.
So what unknown meaning the x2?
The x's.
Yes, okay, excellent.
Yeah. Oh, yeah, that's what we're solving for. So the a's and these right-hand sides, these last terms of b's, those are given. Okay. And notice the b's are numbered just by the equation that they appear in. All right. So we could write out our systems like this, and generally we do for simple examples that just have a few equations in them. But for analysis, this is way too cumbersome. So what we normally do is write this in matrix vector form, or simply matrix form. So we have a vector x prime that has the components x1 prime, x2 prime, down to xn prime, is equal to a times x plus b. So what's happening over here, this part, this is actually a matrix vector product, like the sort of thing you would have done in your linear algebra class. And actually, I need to include the t dependencies in here. So this is a of t x plus b of t. Right. So what you can do is if you're given a system of equations written out like this, long form, you can express it as in this matrix vector form, and you can define what the matrix is basically by reading the entries off of your equations. So a lot of times looking at this form can be helpful for studying or getting insight about the behavior of solutions of the equation, because then we can look at this from a linear algebra point of view. And actually, a lot of linear algebra is going to be playing a role in this chapter. So there'll be a lot of review for you guys, or maybe things that you hadn't been taught at all that now we're going to need. Okay. Now, one thing that's, I'm just going to mention this because it drives me nuts. As far as the lingo, these kind of systems are often simply referred to as linear systems. Like that's the title of the chapter. Although I prefer to call it a system of linear equations, because it's the equations that are linear. But they always call it a linear system, but whatever. So you can refer to it however you want, as long as you reinforce the fact that there's linearity here. Now, some other terminology. If this term is 0, which happens in a lot of examples, then we say it's homogeneous. So it's like how in your first DE class you learn certain methods for solving higher order equations, like for instance characteristic equation and so forth, and you wrote a general solution. And then you threw in an extra term here to make it non-homogeneous, and that's where you needed techniques like undetermined coefficients or variation of parameters, things like that. And actually, those techniques, you'll be able to see how those are derived by what we're going to do here for general linear systems.
Why don't you use the little 3? Why
Oh.
is it equal than, instead of just equal sign?
Yeah, so this is often used, even though I could have simply said equal, this notation is meant to reinforce the fact that it's 0 everywhere. Because if you simply say b of t equals 0, it might be ambiguous as to whether you mean for all t or maybe a single t. But this means, in fact, the way this is often said is, and I never really liked this term, but it's what people say, identically 0. And I never really understood the meaning behind that, like why would they call it that, but because what you're saying it's 0. So you're really saying emphatically it's 0. Also, the 3 equal sign is often used when you are defining something, as opposed to just simply saying two things are equal. Okay.
Why don't you just say it's emphatically 0 instead of identically 0? Because I like that better.
Interesting. I tried at a conference and then that'll make people cringe. By the way,
making up words and terms.
By the way, for those of you who need to know for LaTeX purposes.
It's the equivalent, yeah.
Okay, yeah. Oh, you do that already. Okay.
Yeah, because that's what you use when you do congruences and bond.
Ah.
Equib.
Yeah.
Yep.
The
For
equivalent.
those of us who use that.
Yeah.
Maybe like a tilde, so tilde.
Really for isomorphic.
Isomorphic,
Okay.
all those things.
Well, we're not getting into that here. No modern algebra allowed.
That would be so much cooler than this. No offense.
What?
So
Well,
that would be so much cooler than this.
I know. Yeah.
Sorry.
You know,
No.
I like Wolverine
that's
fans,
strange things.
Huh?
I like the Wolverine fans, but
Sorry, my printout here is like all off. Oh, okay. Yeah, one thing that happens, I've seen this happen when students print something out and bring it with them. If you're using Firefox and you use their like internal PDF viewer and you print stuff out, it often comes out wrong. Like here, I'm supposed to have like brackets for matrix, and they're like just little dashes, little vertical bars. It's completely wrong. So apparently you need to really open up in Adobe Reader and print it.
well, you can use the textbook.
Well, yes, that too.
Okay, some of us don't like to carry a book everywhere. Some of us don't even
I'd
have.
say we're printing out my notes, or
Right.
I was gonna say, I have it just on my laptop.
I just bring this.
oh yeah,
If
yeah.
it's the only thing you're bringing.
Good for you.
Then it's not much effort.
Anyhow, okay. Oops. Somebody tells me I'm gonna be glad that I only have 3 pages of notes. so that I could.
I saw there's like one line on the last page. You should just cut it to 2. Just forget about the last line.
Okay.
It's just my opinion.
What?
I said that's just my opinion.
Oh.
Unless it says free people.
On the notes?
Yeah, when that last page is like a line.
Oh yeah, I tried to like shorten it, but I couldn't really. There was no convenient way to do that. So okay, 2 pages of notes, and apparently at this rate I'll be lucky to get through even those. But well, I mean, first day back after a trip, it's like being hungover without drinking.
So we should just not ever have Monday class if you go back for a trip. For future planning for the spring.
Okay. Well, the thing is, all my classes are on Monday, Wednesday, next semester. So.
So we just don't have Wednesday class after you have a trip. I'm trying so hard.
If you're not careful, I'll bring in Dr. Shu to substitute.
But then I just won't come.
Well, actually, I'm actually doing it anyway because, as some of you know,
Okay, then I'm not coming.
will be Siam linear algebra meeting.
Conference.
Are you guys wanting to go, or I don't?
Are you gonna pay for it?
That's a very
Yeah.
valid question.
Yes.
Yes,
I mean,
yes, the department will pay
That
for
is
it.
the only question. If you're gonna pay for it, I'm gonna go.
Where is this base?
Atlanta,
It's reimbursed.
Yeah,
When
when
you
they
pay
pay
for it, they
What?
reimburse
When
you.
is this?
at the end of the month.
Yeah,
End of
You didn't
October.
know, yeah, but I'll pay them pocket, but they'll pay me.
When is it?
Yeah.
As long as that
It's
happens.
like in 3 weeks,
Yeah.
like the week after fall break.
Yeah,
It's the whole week.
yeah. So sort of very end of the month, and the thing is, I would be definitely missing Wednesday class, and possibly the Monday class too. I'm still waffling about
We
that.
can just have the class on the way.
On
Don't
the
have
way.
class.
Candace will Skype.
Considering only half of you would be there.
Candace,
No.
what you have?
I'll be on the list.
Do you have my son or name?
So I'm not in
Okay.
Zion.
You're gonna say we can
That's
just,
fine.
like, I'll just FaceTime.
FaceTime.
Yeah.
We're trying to figure out
This
this
today.
today.
Well, a lot of people are like.
Skype. Skype.
Yeah, I mean,
Yes, and the thing is, I've already asked Dr. Tian to substitute, and I don't know if I want to bug her again, but, so we'll see.
Oh, no, I'm not recording again.
So we'll see. Now, the Wednesday before fall break class is simply canceled, so.
Yes.
That's exciting.
And I'm trying to get Dr. Dane to cancel class.
Oh,
I'll argue with him so much. I'll argue with Teresa so much.
No, I
about
was
it.
confused about what you already have. Now it makes
God.
sense.
you better, okay, you didn't try to bolster your argument by saying I canceled class, did you? Or
No, I didn't. I did not.
Good, okay, just, because I'm not really supposed to do that.
No, I didn't. I didn't.
Oh,
I
okay,
think
so
we're
this
gonna have
is,
the test on Monday anyway.
Yeah, I know because I fought for
And
it.
then you don't have to even go Wednesday.
It was working in Teresa's benefit. She's like, no, let's still have it Wednesday. And I'm like, no.
anyhow. Alright, so as an example of how system, it's gonna be such a waste of a video. Example of how a system can be written.
I should just not call them.
should be x1. Plus x2 plus cosine t squared. Okay. Now, you can write this as x prime of vector is equal to a of t x plus b of t. So how do you pick out the entries of a and b? Now b is the easier one. We just look for whatever terms do not involve an x at all. So usually written on the end, but not necessarily, but these. Now notice these are definitely nonlinear functions of t, but that's okay. So linearity or nonlinearity is not based on how the equations depend on t, it's how they depend on x. So these being nonlinear doesn't affect anything. This is still a linear system. So if we take a look at what is in the first equation, all right, so we have 1, 2, 1, 2. So we look at, in our first equation, for our first row, and our first column, what is multiplying x1? So we look up here, and we just get a minus 1. Still in the first equation,
2t.
yeah, what is multiplying x2? And that is 2t, and then,
Negative 2t and 1, right?
yeah, so,
T.
yeah,
Thought that was-
minus 2t and 1. So the idea is the ij entry, that is what multiplies xj in equation I. So that's how you pick out your coefficients. And the key is the coefficients must not depend on x's at all. They can only depend, they can be constants, they can depend on t, that's all it's allowed. So that, and if that's the case, then this is I should really call this a of t. Then this is a linear system. Okay. Okay. Oh, I have more notes than I thought. Ah, God. Okay. This is going to be hopeless. All right, but at least I'm getting it. So this is one example of how you write it in that form. But often these systems come about by taking DE that are actually higher order, so maybe they're second order to start with, which usually comes about from physics applications, for instance, and then you go ahead and rewrite them as a first order system like you already had to do on the first homework. And once you do that, then you can describe it as a linear system in this form. For some reason, like it's like this binder is slicker than.
It's usually the blue one I bring.
Oh yeah, that's why. Okay, yeah, this one that's got some real slip and slide on it. Okay.
Do you want to try mine?
It'll be fine. But, so it's still accustomed to the size of it. So.
Bring another chair. Which one's still flag?
Okay. So, for our next example, we have a spring mass system with two bodies that are connected by springs.
Beautiful.
Now, actually, the book worked this out for a case where we assumed everything, all the constants involved were equal to 1. there's really no need for that, but so I'm making it more general. So these bodies have masses m1 and m2, and then the springs have spring constants, like in Hooke's law, k1, k2, and k3. So what we get from Newton's second law, and so force is equal to mass times acceleration, which gives you a second derivative, and also Hooke's law, so that the force of the spring is kx, where k is the spring constant, where that actually the x involved is the displacement. So each xi, we have x1 and x2, one for each of these objects. So x1, for instance, is the displacement of body number I, or body number 1, from equilibrium. So when we're sitting at equilibrium, everything is 0. And then what you can do is like pull on one of these bodies and release it, or so in other words, you're imposing an initial position, or maybe you are pushing it, or you're giving it something in one direction or another, so you're giving it an initial velocity. Either way, that's going to affect what happens here in the displacement of both bodies over time. So from all of these considerations, what we get is, so mass times acceleration for the first body is equal to force from springs. So what we get is, so for a first body, so for instance, suppose you take this first body and you pull on it. Well, this force that the spring is exerting is going to try to compensate for that by pulling back to the left. So we get this minus here, we get a negative displacement. But there's also a force coming from the second object through this second spring. So that would be pulling in the opposite direction. So for instance, suppose you pull this first body, like I pull it to the right, and then I pull the second body even further to the right. So the net effect is for the second spring to stretch. Well, that's going to pull the first body to the right. So that's why we have a force indicating a positive displacement in this case. And then I have a similar thing for the second body, forces on it. So we have, going the other way. So this one is balancing this one. And then I have a force due to the third spring. Okay. All right. All right. So now what you can do is I can express this as a second order system that's in matrix vector form. So I can say x double prime is equal to k times the vector x. So similar idea, I can just see what is multiplying what in each equation, except don't forget about these out here, the m1 and m2. So really you should divide by these first. So what do you end up getting for your matrix is, first of all, in this equation, what is multiplying x1? Well, we have minus k1 over m1 from here. And then over here we have minus k2 over m1. So that's the 1, 1 entry there. And then what is multiplying x2? Well, we have k2 over m1. So everything is divided by m1 for the first equation because I just divide by this first. And then the second row, I have to divide everything by m2. So what you get is, what's multiplying x1? k2 over m2. And then in the 2, 2 spot, what is multiplying, wait, that's multiplying k1. x1, this is multiplying x1. Over here, second equation, what is multiplying x2?
Minus K2 minus K3.
Yeah, minus k2 over m2 minus k3 over m2. Okay, so that's the equation of this second order system. But then what you want to do is rewrite all of this as a first order system. This gives you part of the work that you need. So now, to convert to a first order system, you want to introduce new variables for the velocities. So I'm going to let v1 is x1 prime, v2 is x2 prime. So now I can write out the system in full. So we have x1 prime is v1, x2 prime equals v2, and then I have v1 prime is x1 double prime. So then I can go back to that system there. So I have minus k1 plus k2 over m1 x1 plus k2 over m1 x2. And finally v2 prime is x1 minus k2 plus k3 over m2. So I'm just reading it off that matrix there. x2. So now I have so from a second order system in 2 variables, I now have a first order system in 4 variables. So I can write this as z prime equals a times z, where z consists of all 4 of my variables. So that's x1, x2, v1, v2. And then the right-hand sides give me my matrix. So so for a first equation, all we have is a v1. So now your columns here correspond to your 4 variables in order, x1, x2, v1, v2. So since all I have is a v1 in my first equation, I'm going to put a 1 here, and then zeros everywhere else in that row. For a second equation, x2 prime equals v2. So all I have is a v2, so I'm going to put a 1 here, and then zeros everywhere else. So there's not much going on for those rows. And for the third and fourth equations, I have something times x1 and something times x2. I don't have v1 or v2 at all in there. So over here, I'm not going to have anything. So then these entries, actually this exact same matrix is what goes down here. So I can fill that in. M2. Okay, so now we have this 4x4 matrix that describes our first order system of 4 equations because of our 4 unknowns. Okay. All right, so questions about how we work with these systems and get them in matrix vector form. And there's one more particularly important example. So we have a general n-folder single ODE. So I have nth derivative. So this is an n-folder equation. And then I have combinations of lower derivatives with coefficients that depend on t. And then I have some right-hand side here. That's also a function of just t. So this is a nth order linear ODE. So we can convert this to a first order system, just like let's do all the other cases where we've done this. So I'm going to define n variables. Z1 is x, z2 is x prime, and so on. So each z is some derivative of x. So in general, zj is equal to x j minus first derivative, all the way down to the end. So zn is n minus first derivative. Okay. And now, what we can do is write as the first order system. So first we just reverse all these, or we just look at the derivatives. So z1 prime is equal to x prime, but that's z2. z2 prime is x double prime, that's z3, and so on, all the way down to z n minus 1 prime is equal to zn. So we have these first n minus 1 simple equations, and then finally zn prime, which is the nth derivative of x, is going to be equal to minus all of this. We've got to move it to the other side. So we have, and I'm going to write these in order. So a0, so minus a0 times x, but that's z1. And then minus a1 of t x prime, but that is z2, and so on. So a n minus 1 of t, zn, and then we still have this r of t term that's been sitting here the whole time. Okay. So now I can write this as z prime is equal to a of t z plus b of t. And as for definitions of all of these, so a of t is this matrix where we have, so for instance, z1 prime is z2. So in the first row, because it's z2, in the second position, we have a 1. And everything else is 0. In the second equation, we only have z3. So we have a 1 in the third position. And zeros everywhere else. And this just keeps going all the way down to the second to last row, where we have a 1 in the last position. So we just have 1s all the way down this diagonal that's above the main diagonal, and then zeros everywhere else, until the last row where we have z1 is multiplied by minus a0. Then we have minus a1, 2, and so on, down to minus an minus 2, minus an minus 1. And those are all dependent functions of t, but just for space, I left out the t dependence. So this is an unusual kind of matrix that has all these entries in the last row, and then this super diagonal of 1s. So this kind of matrix has a name. It is called a companion matrix. Okay. And one interesting property of a companion matrix is if you take all these entries in the last row and you make a polynomial out of them of degree n, so this is a constant term, this is a linear term, quadratic term, and then you have a all the way up to degree n, where the coefficient of that is 1. The roots of that polynomial are the eigenvalues of this matrix. So, and in fact, this is what MATLAB does to compute polynomial roots. It actually takes the coefficients of your polynomial and makes a companion matrix from that polynomial and then computes the eigenvalues. It doesn't use other root finding means.
Which polynomial? The one
Yeah, so for instance, if you from this you make a polynomial. So if I let xj, I replace it with r to the j, so just raising a number to a power. So I have a polynomial, I'll call it p of r, is r to the n plus r squared, a2 r squared plus a1 r plus a0. All right. So the eigenvalues of this matrix for each t are the roots of this polynomial. Yeah. So this matrix, a companion matrix, is of considerable interest.
Can you do that in Octave?
Yeah, well, Octave, if you give it a polynomial, Octave will form a companion matrix for you, if you haven't seen, but there also is a MATLAB or Octave function that just produces the companion matrix. I think it's compan or something like that. Okay. Didn't mean to digress like that. And then this vector here, b of t, is a vector that has all zeros except for the last entry, that is this term r of t. That only shows up in the last equation of your system. Okay. And do a simple example of that involving a second order equation. Whoa. Actually, continuing with this example, I guess you could say it's an example of an example. It's kind of like Inception. Actually, also one time I was pretty well convinced I actually had a dream within a dream. It's kind of weird.
You had a what?
A dream within a dream, like an Inception.
I sometimes lucid dream.
Yep.
Yeah,
Sometimes you dream, but you know that it's a dream. Let's call it
Yeah.
lucid.
that's lucid
It's weird, right?
dreaming.
Yeah, it's happened a few times.
It's-
Okay. All right. So this turns into a first order system. Z prime is equal to AZ. So Z consists of X and X prime. So those are your two variables. Your matrix A it's just a 2 by 2 matrix because this is second order. So you just have 0, 1 for your first row, because you start out with your 1 in the second position and then go on down from there. But then your last row are the negatives of your coefficients. So over here we have the negative of this coefficient, so minus 2 over t minus 1 squared, and then here we're negative this coefficient, 2 over t minus 1. Okay. So that's how that second order equation, and we've rewritten as first order systems before. That's not new, but just expressed in this matrix form. You can see how that matrix goes. If I'd had a third order equation, I'd have another, this would be a 3 by 3 matrix, and I'd have 0, 1, 0 up top, and then 0, 0, 1 for the second row, and then negative coefficients in the third row. Okay. Oh, I think I will get through all the notes today. That's good. Now, so some useful properties of linear systems. Okay. So first, you've dealt with, for nonlinear equations, the whole notion of, I think it's something that Dr. Tian covered last week, like a maximum interval of existence. And there were some problems for homework 1 that dealt with that, where there's a situation where first you ask, where is a vector field defined? What's the domain for that? And then what are the domains of your solution for a given initial condition? And the two are not just generally the same. But in this case, in linear systems, they are. So the domain of what are solutions you have is the same as the domain of your vector field. Okay. So you have that compatibility in this case. Because the only way for something to be undefined in your solution is if something is undefined in your coefficients of your system. Okay. So in other words, the domain of your matrix and the domain of any non-homogeneous term you have. Because your vector field is just A of t x plus B of t. So wherever this is defined is where solutions are defined. Okay. Next property. If your system is homogeneous, so I want to emphasize this only applies for homogeneous systems. So x prime is equal to A of t times x. There's no b term, that's 0. Then any linear combination of solutions is also a solution. Okay, and this is called superposition. So for instance, so alpha 1, alpha 2, alpha n are solutions then. So here I'm using a 3 equals another case I talked about defining alpha to be constant times alpha 1 plus a constant times alpha 2 and so on down to alpha n. As a solution of whatever system you have. So that's what superposition means, is combining solutions in this linear fashion. Okay. And finally, there's something we'll get into more later, like in the next section. But we actually have, to some extent anyway, an explicit solution formula. So if you have this general first order system, x prime is a of tx plus b of t, and also if you have an initial condition, so x of 0 is some value c, then the actual solution is equal to some matrix g of t times c plus g of t again, integral 0 to t, g of s inverse times b of s, so b is coming from here. And what is this g? So g of t is called the fundamental matrix of a system. And so one property that characterizes the fundamental matrix is actually a solution of a matrix-valued initial value problem. That so G prime is equal to A of t times G. So it satisfies a homogeneous version of this system, and bound to happen sooner or later. The initial condition is at t equals 0 is equal to the identity matrix.
Remember to x of t or alpha of t.
Sorry, what?
The same thing, like alpha of t equals alpha of the solution.
Often the book uses alpha to refer to a solution, but yeah, this is the actual. It doesn't really matter what I call it. This is the solution. Okay. Now, whether we can find G of t, it depends on the problem. So we may not be able to come up with an explicit formula for a fundamental matrix, but it's quite useful from an analytical point of view. But we'll see in certain cases you can get it. So one well-known example that's very important is, so if A of t is constant everywhere, then the fundamental matrix is simply the matrix exponential of A. So in that case, we know what it is. But if the coefficients of your system are functions of t, if they're variable, then in most cases we cannot get an explicit formula for this, which is quite unfortunate. Okay. So what we'll be doing, we'll be spending a lot of time later in the chapter on seeing in what cases can we get a fundamental matrix, and what can we learn about the fundamental matrix, and what does the fundamental matrix tell us about the behavior of solutions, etc. So fundamental matrix is extremely fundamental to our study of these kind of systems. Okay. Now, this is actually a very important formula to know. In fact, a lot of the solution techniques that you saw in 285, whether it's for first order equations or for higher order equations rewritten as first order systems, if they were all linear, which in that class most things were linear, every single solution technique that you learned, like using the characteristic equation or method of undetermined coefficients or variation of parameters, could all be expressed in terms of this. Everything evolves from this. So, in fact, if you work with differential equations at all, like for your research or take a lot of classes on them, this formula is so important that it just become part of your DNA. It just comes up all the time. Whether it's for designing practical methods. Well, in fact, Haley this morning, this came up in our meeting, just written differently, like with this kept in mind.
Yeah.
And usually it's in this kind of situation where we know that it's the exponential. So it should almost be like a reflex, that you have this kind of linear system, this is our solution, and then working with that. Okay. Now, the last thing I'll talk about is, well, last Wednesday you were subjected to a painful presentation of existence uniqueness theorem. I'm not going to do that here, but I just want to address the whole issue of existence uniqueness, specifically for linear systems, because the theorem that I presented last time, that applies. This is that kind of system. It's just a special case where it's a linear system rather than a general nonlinear one. So really there would be no need to go through the proof again. The book does it anyway, but I figure you guys have suffered enough. And the proof is largely the same anyway. But because it's linear, it's easier to state the assumptions, and also the theorem is actually a little stronger because it's linear. So I do want to highlight that. Okay, so if you have an interval AB, and just for convenience, we'll say that it contains the origin, so just so we can state our initial condition as being at t equals 0. And our coefficient matrix and our source term, our b of t, are continuous on that interval. So that's all we need. If those assumptions are satisfied, then this initial value problem, defined at time 0, and that has a unique solution on that entire interval. Now, so I want to emphasize the difference between this theorem and the theorem I presented last time for nonlinear systems is that theorem only proved that there was a assurance of a unique solution near the initial time. So in some neighborhood initial time, you could show uniqueness. And with some additional assumptions, you could strengthen that somewhat, but that's really all you could do. But because of the niceness of linear systems, if we say that this is our domain on which the time derivative is known to be continuous, then we have uniqueness guaranteed on that entire domain. Even if that domain is the entire real line, we have that. So that's one thing that linearity buys you. I won't really say much of anything about the proof. It really is very similar to what was done last time. And like that proof, it uses the Picard iterates. So t of beta of t is your initial value plus the integral of a of s beta of s plus b of s ds. So one thing that's quite nice is, for instance, suppose that your matrix A is constant. You can pull it out of the integral. Or maybe b of s has functions that you're able to integrate. So you can go ahead and work it out. So you can really work out the Picard iterates to a much greater degree than you could in the nonlinear case. But all the technicalities of a proof, if you go ahead and look at it in section 4.1, you would recognize so many things that were done in the nonlinear case. It seemed like there wasn't any point in subjecting you to that again. Okay, so, well, I've actually come to the end of the notes. because what I'll be doing coming up is talking more about the fundamental matrix. And so, just to be clear, last week Dr. Tian covered the flow of a system. So we're going to work with that definition again, just specialized to the linear case. But just in case it didn't sink in fully last week, I'm not going to really assume that all of that's stuck. So I'll just redefine the flow for the linear case. But at least in that linear situation, things work out a lot more nicely. And then we'll start getting into, in certain cases, how do you go about computing the fundamental matrix that you can use to explicitly describe solutions. Okay, so we're now tiptoeing into linear systems, and we're about to plunge into 3D. We're actually going to spend a lot of time on this chapter. So, and since there are a few minutes left, does anyone have any questions about homework or
Yeah, maybe.
maybe?
Yeah.
Hold on, let me look. It's the 2.1, that one, you just want us to draw the little approximation, right? I mean, that's really all
Write
we
it
have
out,
to do.
right?
What?
Like, write them out.
Yeah, you have to like.
Let's see
you
what.
have to-
Yeah,
The problem one.
yeah. Like, I mean, okay, my question was, you want us to draw that out, or can we do it in MATLAB?
You can do it. Yes, you can use MATLAB, but
Yay!
so because I do want to see like the actual numerical values, since that's something that for this kind of system can be worked out. Well, you would need that to draw it anyway.
So we wrote them out.
Yeah.
And it took like hours.
Really?
No, not hours.
To compute them.
Well, for instance, in part A, you're doing 4 steps,
Yeah, and
and then
10, wait,
No, then-
4 steps and then
10
10
for the
steps.
other-
The
Yeah.
10 takes longer than you think it would.
okay.
4 and 10 and then 5 and 10. So it's like 29 steps
Oh,
altogether. Right?
sorry.
It's okay.
Bill's character.
Right.
Okay, so we can't just like list the values in MATLAB and just call it, and then have it, like, okay, never mind.
Well, I mean, if you really want to write the code to do that.
Maybe.
Yeah, at this point, probably if you did not write it by hand, I'd recommend not writing it.
No, I think I've done like part of the first one, and I think that's it.
Yeah, I did the first one. I was like, go back to the second one.
But then, yeah, 2.
Makes me appreciate the computers do all of these things.
The 2.4, the 1A part, the limit cycles, where you set the limit equal to 1, right?
Yeah.
Equals to 1. We did like, integrate both sides and then
Okay. So.
I feel really embarrassed to ask you like how to integrate stuff, but it doesn't like eat a lot of things and it doesn't check out.
Okay. So you're talking about like solving that first equation, the R.
Yeah.
Okay. That's worth talking about. So it's R prime
Yes.
equal
Because it
to
was
1 minus R squared.
no R squared times R.
Okay.
Yeah. Inside, yeah. Yeah.
Okay. Now, as the book mentions, this is a separable
Yes, it is.
ODE. Okay. So you would solve it like that. Okay, so that's where the difficulty comes out, how to do that integral.
Yeah, and I looked online, partial fractions.
Yes, it's partial fractions.
Partial fractions.
And what will be helpful to do after you carry out the integration, because you're going to get 3 logarithmic terms,
Right.
and then combine those into 1 log.
So you get a e. Yeah, we can combine, and then it will be like e to the power of those guys.
Yeah, and then exponentiate both sides, and so then you're going to have something equals e to the t.
But then we'll have t plus c, right? Like a constant
Oh,
C1,
yes, it will be,
Or
yeah.
like,
Yeah.
yeah.
Oh, what you can do though, let's see, for this one, there's no initial condition given, right?
They want to get the value of R0 equals R0.
Yeah.
But then we have to solve R first to get R0 equals to R0, right?
Okay, yeah, let's see. Okay, so you can plug in t equals 0, and then solve for c to get
Yes.
R naught. Okay, and now the thing to keep in mind is, okay, so now R naught it's any value that's not equal to a fixed point. So it's not equal to 0, 1, or -1. And you're supposed to show that as t goes to infinity, alpha t goes to 1. Now, okay, so then what you can do is you get the solution whatever form is convenient. I mean, if you could solve for r as a function of t, that's the ideal thing. It's doable. It's just kind of a pain. Yeah, and then the thing is, what happens is you have all these exponentials in there, and are we going to infinity and so forth, and just show what the limit is 1.
And solve for R by solving that, right? And then
Yeah.
you want to plug in, you want to set t equals 0, and then you got R0 in terms, well,
To get the value of c.
R0,
Yeah.
Right. Okay, it's hard, but good.
Okay. Anything more in the last 3 minutes?
Maybe before 7 o'clock.
Okay. Fine, well, I'll be at home working on the notes for the next section. Ugh. Well, actually, right now I'd rather just pass out. But okay. Well, I think it's time to call it a day. Well,
Monday night.
most of you have started career analysis now, but I guess 5 out of 6.
I don't,
Okay. Oh yeah. Twice a week you're being me for class.
when did you get back? Like tonight?
Last night at